So today's goal is to cover the third law, Newton's third law. For every force, there's an equal and opposite force. And remember, we're trying to stay away from for every reaction, there's an equal and opposite reaction. Force is a better way to think about it. So let's say we have a runner. Well, we know that the runner is moving forward. So there must be some forward force on the runner. That's caused, between friction between our running shoes or sneakers on the ground. But believe it or not, there has to be an opposite force. And the opposite force is a push on the earth. When we walk or run, we push back on the earth, on the ground. So yes, the runner actually pushes on the earth. But of course the question is, well, why does the runner move more? And that kind of gets to our F equals ma. The runner's mass is going to be 60 to 80 kilograms probably for an adult. The mass of the earth is immense, and I hope we get to that if we talk about gravitation. So the acceleration on the earth is minuscule, is tiny, tiny. There's always the question, does the earth move at all? Probably not, because probably while you're running forward, somebody else is running in the opposite direction, and it kind of all cancels out. Also, the earth can compact a bit, which takes some of that force away. So here's a rocket, and the rocket goes up because of the third law, excuse me. But one thing that I think is confusing, and we might think, oh, well, the gases are pushing against the earth, and that's why it goes up. But if you notice in that picture, in that little GIF there, the rocket's still going up while it's way, way in the air. It's not that it's pushing against the earth. It's simply that the gases are going in this direction with a force, and they give a force to the rocket in the opposite direction. And the best example of this, and you probably saw the movie, is WALL-E. When WALL-E was out floating away from the spaceship, and he was in some danger of getting back not going back to the spaceship, he had his fire extinguisher. So WALL-E must have really paid attention during his physics lecture, because he knew that if he put the gases out away from the spaceship, there would be an equal but opposite force pushing him back towards the spaceship so he didn't float away and die in space. Usually physics or movies get the physics very wrong, especially science fiction and superhero movies. And that's not why you're going to the movies. I understand that. But in this case, the screenwriters really did get the physics correct. And I thought that was great for WALL-E. Here's another example, and it seems kind of crazy, but it would work. If you were on a sled on ice, and you had bricks on the sled, I don't know why you would do that. Maybe you were taking the bricks to some place to build something, and you got stuck. If you throw the bricks away, your sled will move in the opposite direction, because for every force, there's an equal and opposite force. I know I didn't draw I should really draw the arrows about the same size. Wouldn't be a bad idea. So if you were really clever, you could just throw all those bricks onto the ice and move yourself off the lake, and of course hope that they don't break through the lake. Now the math that we're going to take a look at today has to do with mass and weight. So mass is the amount of matter in an object. Mass does not depend on gravity. It's independent on gravity. So you and I have a certain number of atoms in our body, and that's what we have. If we go to the moon, we still have that same number of atoms in our body. Mass never changes. You might say, well, what if I go on a diet? Well, just in general, mass doesn't change unless you go on a diet or you put on weight or something. And the English unit of mass is a slug. So it's really kind of weird. If you see on the side of a cereal box, it'll tell you how many grams are in there and how many pounds or ounces. It really shouldn't do that. The comparison unit is the slug, but they're not going to put how many slugs are in your cereal box or your oyster crackers or cookies or whatever you like, because people don't like slugs. But that is the English unit of mass. weight does depend on gravity. It's the force from gravity pulling on an object. And weight is mg. That's actually not a new formula. F equals ma. Well, if we're talking about gravity, the acceleration is 9.8, which is g, so we just call that weight. I try to write Wt rather than W because W is work, and that's a really important thing later. And the English unit of weight is a pound. So pound is equal to 4.45 newtons. Or the way we think about weight more often is in terms of pounds and kilograms. So if you take your weight, and we all know our approximate weight, and divide by 2.2, you should get your kilograms. So it's always less. So if you want to feel more slender, take your weight, divide by 2.2, and say, hey, I'm only this many kilograms. Maybe you're only 50 or 60 kilograms. You'll feel great about yourself. So these problems are really pretty easy and pretty straightforward. So what's the weight of a 60 kilogram man? So weight is mg, and we just substitute. Just about anybody can do this. And we figure that out. So if the man is 60 kilograms, he's 588 newtons. And that's roughly my weight. Might be a little bit less than that, but somewhere in that ballpark. Now remember, where do we get the newtons from? This is kilograms. This is meters per second squared. And a kilogram meter per second squared is a newton. Next one is also really, really easy. The student weighs 500 newtons, and we want to know, well, what's her mass? Since we're after mass, we'll divide by gravity. It's easy enough to do the algebra first here. In fact, I'm going to write that newton as a kilogram meter per second squared, because we're going to divide by 9.8 meters per second squared, which is gravity. And those cancel. And we get 51 kilograms. Yeah, that's pretty reasonable.